Hello, all. Welcome back. Video 2 for section 4.4, the coordinate mapping. So for an abstract vector space V, the coordinate mapping, which takes a vector and replaces it with, sends it to its coordinates in Rn, connects the possibly unfamiliar vector space V to the very familiar vector space Rn. And this next theorem says essentially that there's no information lost in doing so. So if we let V be a vector space and let B be some basis for V, then this coordinate mapping that takes a vector x and v to its coordinates in Rn is 1-to-1 and onto. So it's 1-to-1 linear transformation from V onto Rn. So let's look at an example of this happening for a truly abstract vector space. So let's let p1 of x be the polynomial 1 plus x squared. Oops. P2 of x is going to be x minus x squared. We'll take P3 of x to be 2 plus x plus 3x squared. So let these things be polynomials or vectors, if you like, in P2. We'll let our B be the standard basis for P2, 1x and x squared. The first thing we'll do, let's find the coordinates of P1 with respect to B, the coordinates of P2 with respect to B, and the coordinates of P3 with respect to B. Once we do that, we'll use 1 to determine if P1, P2, P3 is linearly independent. In P2. Okay. Okay, so what do we know? Well, so for the solution, we know exactly what these coordinates are. So, right, this should be like C1, C2, C3, where we want P1 of x to be C1, our first basis vector, 1, plus C2, our second basis vector, plus C3, our third basis vector. But we know exactly what these coefficients are. We literally read them off of the expression of P1. So this means that C1 is equal to 1, C2 is equal to 0, and C3 is equal to 1. And so we get that the coordinates of P1 relative to B, just the most obvious thing, 1, 0, 1. And similarly, the coordinates of P2 relative to B or what? It should be 0, 1, negative 1. There's no constant term. There's one x term, and there's negative 1 x squared term. 0, 1, negative 1. And the coordinates for P3 relative to this basis should be what? 2, 1, 3. Okay, not so bad. And then what? So for part 2 now, so by theorem 4.8, this collection P1, P2, P3 will be linearly independent if and only if the corresponding coordinate vectors are linearly independent in R3. This is a linearly independent set. If and only if the set P1, B, P2, B, P3, B. Oops. is linearly independent in R3. Okay, and we know how to tell if vectors in R3 are linearly dependent. But yeah, notice these coordinates have changed the problem from an abstract vector space P2 into a problem in R3. So as always, we want to solve C1 P1 B plus C2 P2B plus C3 P3 B is equal to 0. We know that by the inverse matrix theorem, we don't even need that. By definition, linear independence comes from whether or not we can find a non-trivial solution to this equation. And so what we need again is what? Is some matrix C1, C2, C3 is equal to 0, or really we can write the vectors in 0, 0, 0. And that matrix is going to come from P1, P2, P3 for its columns. So this is 1, 0, 1, 0, 1, negative 1, 2, 1, 3. So once again, we are row reducing a matrix. Like I said before, everything comes down to solving systems of linear equations. Okay, so we want to row reduce 0, 1, 2, 0, 0, 1, 1, 0, 1, negative 1, 3, 0. And I'll let you check this. Reduces to 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0. I'm sorry. That's a keep on doing it. That's a 0 here. So this is giving us, check. You should check this step, but this is giving us a unique solution. And we know that one solution already exists, the trivial solution. So the trivial solution is the only solution. And so what does that mean? Well, it means that C1 is equal to C2 is equal to C3 is equal to 0. So those vectors are linearly independent. Oops. Dependent. And that means that the polynomials must also be linearly dependent. So P1 of x, P2 of x, P3 of x must also be linearly independent. Okay, and then yeah. Okay, and so then we can use the we can use the invertible matrix theorem also to show that these three must also form a basis, but that's of P2, but that's neither here nor there. Okay, that's all we had planned for 4.4. I'll see you next time for 4.5. Take care, everybody.